Hello everyone, welcome to my presentation. My topic today is related to operating system kernel, memory access, mapping, parsing, and race condition issues. The title is Racing the Dark, a new TOCTTOU story from Apple's core. TOCTTOU is short for time of check to time of use. It's kind of race condition issue. My name is Wang. I can be reached through this email address. This research is the third kernel security research project I made public in 2020. The first two projects are related to the Bluetooth and the Wi-Fi subsystems of macOS and iOS. Today's content can be divided into 4 parts: background knowledge and the TOCTTOU vulnerability, Project Kaimong, kernel vulnerability case studies, and the end. In the first part of the presentation, we will focus on the background knowledge of user mode memory access and the kernel race condition vulnerability. So let's start. When developing operating system kernels and the drivers, functions related to user data mapping, accessing, parsing are often found vulnerable. In order to solve this type of problem, almost every system defines standard operating rules when touching a trusted user input. In this section, I will list the user mode memory access methods of Android Linux, Windows, and macOS iOS platforms, as well as some real-world vulnerability cases. So let's start one by one, case by case, from easy to hard. The first platform is Android Linux. In my opinion, the Linux kernel API document is worth reading. The first chapter of the document is named Memory Management in Linux, in which user space memory access describes in detail the API set that should be used when accessing untrusted memory. For example, the well-known functions copy from user and copy to user. Their explanations can be found in the links below. If these rules are violated when accessing user data, the vulnerable function will at least introduce a local privilege escalation vulnerability into the kernel. The simplest but real case is as follows. I found this vulnerability when I was working on mobile security research 7 years ago. We can still find the leaked source code on GitHub. This vulnerability is located in the MediaTek SD card driver. Due to lack of restrictions, user mode processes can open and operate this driver. Through auditing the leaked source code, we can find that almost every I/O control handler of the driver has problems. For example, in line 994, the function copy from user mistakenly trusted the length of input. The size of the buffer on the local stack is only 25 bytes, and such a copy means that stack-based buffer overflow. In general, this vulnerability gives you a chance to be guarded. Of course, all of this is based on the fact that 7 years ago, there was basically no mitigation mechanism for mobile phones. But this simple exploit took me a lot of time. At first, I found that no matter what I tried, I could only get my phone restarted. So I had to re-examine the last written instruction of the vulnerable function. Without the help of kernel debugger, I guessed one by one about the possibility of overwriting the registers. Destroying the blue register like R4 or R5 may cause the caller function to crash. Because the value in this register may be the base address of an object, for example, and we cannot just rewrite it. Destroying the green PC register means we need to figure out where to put the shellcode. The good news is that security features such as PXN were basically not enabled on mobile phones in 2018. With the deepening of the analysis, I found that the red SP register is the key to the problem. I broke the SP address before handshking the return address. So why is the SP register so critical? The answer is related to current thread. In order to improve speed, each operating system uses the simplest method to locate the current thread structure. For example, the Windows kernel determines current thread based on the fixed offset of the FS register, while in the Linux kernel version 2.6, current thread is located with the help of the SP register. Therefore, once the Stack Overflow corrupts the SP register, it will cause serious problems during context switching. That's why I have to turn off interrupts in the shellcode first. The next question is where we should return to after the shellcode is executed. The problem is not difficult for us, I think. We need to search the code segment, find the return address of the BL instruction, and then redirect the execution flow of the exploit to that location. In this way, our code can be executed stably. The following figure shows the complete process of vulnerability exploitation. First of all, we need to select the appropriate value of R4, R5, and other registers, and select the appropriate address to place shellcode. Once the shellcode is executed, we need to turn off system interrupts at the first time, and then search the double-linked process list to find our own task structure. By locating the correct SP offset through signature search, for example, we can restore the SP register. Then we can re-enable the interruption and complete the process of escalation. The last step, we need to search the correct return address and exit. By the way, we don't have the kernel debugger, and we cannot print out debugging information because this will cause context switching. So this page contains a 7-year-old screenshot of a successful EOP, privilege escalation. To avoid trouble, I removed the name of mobile phone brand. The vulnerability is actually caused by third-party vendors' SD card driver. This vulnerability affected many mobile phone brands at that time, including Samsung, Xiaomi, Huawei, and so on. In the third part of this presentation, we will see other vulnerability cases caused by graphics card supplier. As a summary of the Android Linux part, I would like to make a few points. Number one, all input is harmful. For the vulnerability mentioned earlier, I think every kernel programmer should try his or her best to avoid making such mistakes. Number two, stack-based buffer overflow exploitation in real world is not as simple as in books, especially when you don't have a kernel debugger. Number three, you may be wondering, do Stack Overflow vulnerabilities still make sense today? I would like to give 2 examples on this topic. The first one comes from the presentation of Pangu team, Wang at Black Hat USA in 2019. The title is Towards Discovering Remote Code Execution Vulnerabilities in Apple FaceTime. On page 101 of the slides, TLA discovered some cases of Stack Overflow caused by the compiler's incorrect insertion of stack canary on ARM platform. The second example comes from my presentation at Black Hat USA last year. The title is Dive into Apple I/O 802.11 family version 2. I found a case where the compiler did not insert the stack canary for the target vulnerable function. The ID is CVE 2020-9899. I think after reading these presentations, you may have some different ideas about stack-based buffer overflow. The next platform is the Windows kernel. I would like to share some more interesting cases with you. First of all, there is a slide called Common Coding Errors that is worth reading. It contains most of the common kernel programming errors and solutions. As a part of the user data processing rules, routines such as prop for read and prop for write are APIs that we must use. Their explanations can be found in the links below. Similarly, if these rules are violated when accessing user data, the vulnerable function will at least introduce a lock privilege escalation vulnerability into the kernel. In 2012, I mentioned an interesting feature in the Win32k font engine in my font security-related presentation at the Syscan 360 conference. For efficiency reasons, font file will not be copied into kernel mode. So how does the kernel scalar engine access this data located in user space? The answer is that the engine will access and manipulate this data directly. In the figure, we can see that the return value of the routing pway get pointer callback is a user mode address with length of 4E8, and the address here is a user space address. And all subsequent parsing operations are based on this user mode address. So in my opinion, this design and the implementation give TOCTTOU, or risk condition vulnerability, a large living space. A year after, Juro from Google Project Zero released his BoxPom on GitHub. This amazing tool found a large number of kernel double fetch and risk condition vulnerabilities. Some of these records can still be found on Google Docs today. BoxPom can record all access actions of the kernel to user mode data, and vulnerability types like double fetch will have nowhere to hide. Then Juro turned his research direction to the Win32k font engine, and again his tool found a large number of double fetch and TOCTTOU vulnerabilities. I listed some of his blog here. If you are interested in font security, this blog should not be missed. These excellent studies keep me thinking, what else can I do? In general, there are only 2 ways left. The first way is to improve the code coverage rate during vulnerability hunting, and maybe I can find some missed cases. And yes, I did. The other way is that I must try to find some new vulnerability patterns. So I shared my approach in the Black Hat USA 2014. My slides can be downloaded in the first link here. In short, I mainly did two things. I compiled the font security engine in the kernel of the leaked Windows NT source code. Yes, it can be compiled. I compiled, actually recompiled all project codes into a static library in user mode. Then I wrote a corresponding application to drive it to work. And then I uploaded the project to GitHub. Because I recompiled, repackaged the source code, my slides should not be put on the official website of Black Hat. But I think the whole process is very interesting. For example, on the left, I can get all the symbols of the font engine. And I can also see how each glyph is rendered in pixels. It's very interesting. The second thing is that I did find a new type of vulnerability. Its ID is CVE 2014-1819. Because the font engine introduced a caching mechanism in Windows XP, I found that the logic of many kernel routines has become, first, go to query the font cache. Here we can call it the first fetch. And then the kernel buffer is allocated according to the size of the first query. Next, access to user mode data to initialize the kernel buffer, which we can call the second fetch here. As you can imagine, there is a huge time window here. Any inconsistency between the first fetch and the second fetch will result in heap out-of-bound access. This vulnerability pattern can perfectly avoid box pawn scanning because there is only one user mode read or fetch in the entire process. As a summary, I want to say again that all input is harmful. And the new features or changes always means new attack surfaces. The font cache introduces new TOCTTOU vulnerability to the kernel. These non-traditional double fetch vulnerabilities are difficult to capture. The third platform is the macOS iOS kernel. On macOS iOS platform, the situation becomes a little more complicated. Functions like IO connect method can automatically handle user input for the kernel and extensions, while BSD functions such as copy in and copy out provide support for manual operations. In the link above is a document called Kernel Programming Guide. Although some of the content in the document is out of date, but I still recommend kernel developers to read it as a reference. For the more commonly used IO-kit functions, I have listed some links such as IO connect call method. Inside the IO connect call method function, many code branches are related to the class IO memory descriptor. So I also listed the IO memory descriptor documentation below. Next, I would like to refer a blog post by KingLab, Tencent Security. This 4-year-old blog explains in detail a vulnerability pattern related to memory mapping in the macOS iOS kernel. The idea of the vulnerabilities include CVE 2016, 17.6, 20, 24, and 25. Regarding the topic of memory-related vulnerabilities, Ian Beale has a blog in 2019 that I have to mention. If you are interested, this article is also worth reading. Today, due to the limited time, I have to limit the discussion to the first King Labs blog. For friends who have not read this blog, I will use the simplest words to summarize the root cause of these TOCTTOU vulnerabilities. Inside the IO connector call method function, the user mode input will be processed if the input user data size is less than 1 page. This function will use memory copy to copy all the data into the kernel. The problem is that if the input data is larger than 1 page, IO connector call method will create a memory descriptor to describe the target data. And at this time, the user process still has write permission to the mapped data. So let's think about it. What does the write permission mean here? It means TOCTTOU attack. So in this blog, Arthur also gives Apple's fixed solution, which seems to be related to the VM_copy flag. If you are interested, you can read the then source code on GitHub. As a summary of this section and the first part, I would like to say, penny, all inputs are potentially harmful. One more thing is that, does the security update really work? I mean this one, the macOS one. Can it cover all corner cases? I don't think so. We will see that. After seeing this, you might say that these cases are not the latest vulnerability. They are just some end days, not 1 day nor 0 day. I would say if we want to find more interesting vulnerabilities, we must have powerful tools in hand. Here I would like to introduce Kaimong to you. In this chapter, I will explain what Kaimong is and what problem can it solve. Kaimong is an open source pre- and post-callback-based framework for macOS kernel monitoring. Its source code can be found on GitHub. Kaimong includes many useful features like file, process, network traffic monitoring, dynamic library and kernel extension monitoring and blocking, mandatory access control policy filtering, and so on. In addition, Kaimong also integrates a kernel inline hook engine, through which we can hook almost any kernel function we want. Some of the above functions are not that easy to implement. For example, for file and process operation monitoring, Kaimong's solution is based on the chaos KPIs, but the chaos has many limitations. For file operating, the chaos callback cannot distinguish whether the operation is create new or open existing. For process creation, the chaos callback cannot get the command line parameters. This is unacceptable for kernel monitoring. But all of this can be easily solved. This screenshot is to locate the command line information by searching call stacks. Another interesting topic is related to mandatory access control policy. The security implementation of macOS iOS almost all relies on the mandatory access control mechanism. So is it possible for us to dump the kernel's MAC list? A potential issue of these requirements is how to obtain unexported logs and access kernel data structure safely. Such challenges cannot stop us. After reading the kernel source code, I found that there are two callback opportunities for the third party between the code that obtained the mutex lock. This means that I can safely access and dump MAC-related data structures in the callback functions. For kernel inline hook engine, it will insert pre and post callbacks for the target function. In the pre-callback handler, we can filter the input parameters, and in the post-callback handler, we can modify the return value of the function. This screenshot is an application of Kaimong kernel inline hook engine. I hooked up functions related to kernel extension loading, unloading. You can see that I parsed and filtered the input parameters of the function in the pre-callback handler, and I can even patch the target kernel extension. With the powerful support of Kaimong, I built many sniffers and fuzzing tools. Last year, I published two research projects, one related to Bluetooth security and the other related to Wi-Fi security. They were presented at Black Hat USA and Black Hat Europe conferences. This is a request sniffer for IO 802.11 family. We can see that the kernel receives a large amount of user data from the daemons such as airport D. Airport D is very important user mode daemon of Wi-Fi subsystem. Some of the request data contains complex formats, and I have reported about 18 kernel vulnerabilities, some of which have been fixed. And this is a sniffer for IO Bluetooth family HCI requests. We can also see that the kernel receives a large amount of user data from the daemon Bluetooth D. More complicated is that third parties can customize their own vendor commands, and most of these commands are not documented. I have reported about 23 kernel vulnerabilities last year, and some of which have been fixed. With the help of Kaimong, I hooked up almost all kernel mapping related functions. This engineering practice have given me a better understanding of the implementation of kernel mapping. And these sniffers can be easily transformed into fuzzing tools. And in addition, last year I also implemented a simple kernel address sanitizer. It's still not perfect, but it does work. Yeah. The next part is the latest kernel TOCTTOU vulnerability case studies. Last November, Apple fixed at least 2 GPU graphics card vulnerabilities that I submitted. But I only got one CVE ID at the moment. The ID is CVE 2020-27914. And the pattern of this vulnerability looks like this. The driver trusts the user mode input by mistake. And the fatal thing is that this input is directly related to the number of kernel loops. So such code means heap out-of-bound access, read and write. So in summary, it seems that the root cause of the vulnerability is related to the lack of effective input validation. And this type of vulnerability can be easily captured by kernel address sanitizer. And you will see why I used the words "it seems that." Next, let's look at the patch for this vulnerability. It is not complicated. The number of loops is limited to a fixed value here. Before the loop starts. This time, everything looks fine. But let's think about it more carefully. There are two questions I leave to you. Is it possible for us to bypass the security update 2020-007 and re-trigger the vulnerability? And also, input buffer is on the kernel heap. Is it possible to race against it from, for example, user mode? The answer is yes. I have a demo for this. Okay. Yeah, today is the March 29th. It's already Monday. Yeah, today is Monday, and the latest version of macOS Big Sur is 11.3 beta 5, and the build number is 20E5217A. Yeah, and the kernel version is the latest one. Please allow me run my POC, my fuzzing tool. And we can see that after a few seconds, yeah, we can see that the operating system has crashed. Yeah, I actually prepared two versions of the slides, the current version and more complicated version. Since Apple has not fixed this serious vulnerabilities, I cannot share the details with you yet. And here is a summary of the patch bypass. As the vulnerability has not been fixed, please forgive me for not disclosing the details of the vulnerabilities. I will write a blog post after the patch released. TOCTTOU vulnerabilities such as CVE 2020-27914 have been hidden in plain sight for a long time. And even after I submitted the vulnerabilities, they were not correctly identified by the developers. This led to the patch can be bypassed. Okay, the end, last part. From the perspective of security research, I would say the first one, vulnerabilities like 2020-27914 and 27936 have been hidden in plain sight for a long time. They remind us to re-examine the kernel memory mapping mechanism of macOS and iOS. And number two, sometimes the security patch can be bypassed. Yeah, in the Black Hat Europe presentation I presented, I have another example. It's a Bluetooth HCI subsystem example. I can bypass the patch. So understanding the implementation of patches is often helpful for vulnerability research. And with this research as a new starting point, I believe we can do more. And from the perspective of security engineering, I would say with the help of Kaimong project, I believe we can do better. Yeah, thank you. Thank you very much. Thank you for your time. Bye.